Right, hello everyone. This is our second lesson for networks. So this particular presentation is called Graph Theory. So again, with the recap, you're going to have to refer to the OneNote page that I set up, which has the previous examples. Just a very quick recap from yesterday, the previous lesson. So key terms. So again, the dots are called vertices, and if there's just one, it's called a vertex. So you can see here we've got a 1, 2, 3, 4, 5, and 6 vertices there. So the lines or connections are called edges and arcs. So again, there's one there as well. Okay, so this one has 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we've got, in terms of the regions and faces, so for this network, there's 1, 2, 3, 4, and then 5 on the outside. So remember, we're including regions that are outside the network as well, not just the ones that are closed in. So a new term that you need to get familiar with is a loop. So if an edge starts and ends at the same vertex, so here, this particular thing there, that's another loop there, it's basically called a loop. All right, so it's basically a circle, okay? And there it is there, just a little bit bigger. Multiple edges. So when two edges or arcs have the same origin and destination vertices, they are called multiple edges. So we can see here the blue. So we've got A3 and we've got A2 there. They're basically, they're called multiple edges because they start and end at the same vertice. Similarly with the red, so that's A5 and A4. They both start and end at the same spot as well. A weighted graph is basically the edges or arcs have a weighting, all right? So in this case, a value. So here the vertices may represent towns or landmarks or something like that, and each of those edges represent a road that's for A to B is 10 kilometers long, A to C is 7 kilometers, 9 kilometers between B and C, so on and so forth. So each edge has a weighting, so it basically has a measurement there, so which indicates that it has weight. A directed graph, well here you can see an undirected graph. It just looks like your normal network. Okay, your directed graph actually has, if you see here, it has directions. So it indicates that it's going in a certain manner. A simple network graph is one which is unweighted with no loops and no multiple edges. You're probably thinking, what does it look like? So we've got this thing here where it's unweighted, no loops, and no multiple edges. So this is a simple network graph as it has no weights, no loops, and no multiple edges. The graph here is not a simple network as it has a loop, okay, and the loop's right over here. This is not a simple network as it has a weight. Now it's pretty much the same network as this one here, except now that it has a weight to it. So all of these measurements, it's therefore classified as a, sorry, it's not classified as a simple network. This is also not a simple network because it has multiple edges. So we've got a starting vertex there and an ending vertex there, or vice versa. And we've got one arc on an edge going that way and another one going that way. So we've got two vertices there. Sorry, two edges going from the same vertices. So this is a simple network as it has no weight to it, has no loops, and no multiple edges. All right, which is a bit counterintuitive, but it actually fits the definition. A walk. So for the network on the right, A, C, D. So we're going A, C, D is referred to as a walk. Okay, so basically it's just following a particular path. We could also take the road A, B, C, D, okay, which would also be a walk. Because we've started in one spot and ended on another, this is called an open walk. Okay, so here we've gone this way, so that's called an open walk. Similarly, if we go, let's go with blue, if we're going this way, that is also an open walk. A closed walk would be one where we start at one spot and end up on the same spot. So if I go A, B, C, D, and then back to A, that's called a closed walk. Now here's a path. If we take the path A, B, C, D, this is an open path. We take the path A, B, C, A, that's called a closed path. This is sometimes referred to as a cycle, okay, because we're going this way, that way, and then back down. The length of a walk, cycle, or path is determined by the number of edges it uses. So here, the path will be A, B, C, D, which has a length of 3. There you go, there's a Millennium Falcon. So it took 1, 2, and 3. If I do A, B, C, D, C, it has a length of 6. So A, B, C, D, and back to C. Trail. A trail is basically a walk with no repeated edges. The following are trails. A, C, D. Now let's pick a different color. A, B, C, D. And then we've got, let's go with red. We've got A, B, C, back down to A. A, B, C. So let's do this again. So we've got A, B, C, D, back to C, back to B, back to C, is not because it has a repeat edge. A trail versus path. All paths are trails, but not all trails are paths. With paths, we can have multiple edges. With trails, we can not. If a trail starts and ends at the same vertex, it is called a closed trail. So A, B, C, A. Okay, so we're going A, B, C, and then back down to A. Connected vertices. So two vertices are connected if there is a path from one to the other. So in this particular case, AB is connected. AC is also connected. A to D. So to get to D, I can go via C down that way. Okay, if I want to go A to E, I'll go a different color here. I can go that way, and then that way. All right. So I've got all the possible listed connections there. Adjacent vertices are two vertices where one is connected by one edge. It is called an adjacent vertex. A to B, all right, they're adjacent vertices. B to C, there's another one. A to C is another one. C to D is another one. D to E is the last one there. A connected graph or network is one which is connected. I know, I was surprised too. So here all the vertices are connected. Okay, so I've got F is connected to G, to H, and to I. Another example. An unconnected graph. So we've got J here. He's a bit of a loner. Excuse me. So yeah, he's just this is classified as unconnected because it is not connected to anything. This is called an unconnected or disconnected graph / network. A complete graph is one where every vertex is connected to every other vertex via one single edge. All right, so there's an example of one. So A to B, so they're both connected. There's another example with A, B, C. So A is connected to B as well as C. And then we have B, which is connected to A as well as C. And then lastly, we have C, which is connected to both B and A. Here again, we've got A, which is connected to B, C, and D. And then we have B, which is connected to C, D, and A. And then we've got C, which is connected to B, A, and D. And then lucky last, D, which is connected to C, B, and A. And here we've got a five-sided shape. So we've got a pentagram there. So as you can see, A is connected to all the other vertices, B is connected to all the vertices, as is C, D, and E. So a complete graph with n vertices is denoted as Kn. What's the n stand for? It's just the number. So we've got K2, K3, K4, K5. In a connected graph, if an edge is removed and the resulting network becomes disconnected, it is called a bridge. You're probably wondering what's he talking about. So this is something very similar from your textbook. So I've got A, B, C, D, E, and F there. C to F, all the vertices are still connected. Okay, so it doesn't really cause too many issues. Similarly, if I remove E to F, the network is still connected because all the vertices are basically connected off, and I don't have a vertice by itself. Again, if I were to chop off DE, all the vertices are still connected because I've still got a connection there, still got a connection there, still got a connection there, and obviously these two are still connected. Now, even if I were to get rid of this line here, it'll still be connected because, let me get a highlighter, because this is still there. I can still connect to that, that, and that. So all the vertices are still connected. Now, if we removed BC though, these two vertices are no longer connected to this larger network here. Okay, so it's actually disconnected. So therefore, if we remove BC, A and B are no longer connected to the network. The same applies to AB. So if I no longer have that, then I've got A by itself. So A doesn't have any connections at all. So therefore AB and BC are classified as bridges because if we get rid of them, we have, think of it like we'll have an island almost, okay? I've called this Castaways. I don't know if you guys can, I just want to point out Wilson's right there. If anyone can see Wilson. Can I get you guys to start working on exercise 5B now? All right, thanks for paying attention. I shall see you next time.